I think it's great. Okay. This is number 4 from 21A. So we have a U.S. Navy plane, which uses electromagnetic catapults to launch planes from aircraft carriers. They're sometimes called railguns. Have you ever heard of them? Yeah, they're pretty cool. Maybe we'll look up some videos of railguns. So they basically use a series of electromagnets to accelerate, in this case, the planes off an aircraft carrier. They accelerate a 45,000 kilogram plane up to 260 kilometers per hour, which is pretty amazing. An electron, which you need to know the charge on an electron, you could have looked that up, is going at 260 kilometers per hour, perpendicular to a magnetic field. You know the force. What's the field strength? So if you have velocity, here, by the way, here's the 2 equations for interacting forces in magnetic fields. Current times the length of the wire in the field times the strength of the magnetic field, or F equals Q V B. They are the exact same equation. It's just that this is charges per second. So this is just rewriting it in terms of charges, okay? Since this was an electron, we're going to use this version of this equation. So the charge on an electron, 1.6 times 10 to the negative 19th coulombs. It's going to be moving at 260 kilometers per hour, because you have to look it up. Sorry about that. Well, and Einstein would have known to look it up. And the force that's produced to make that electron accelerate is 3 times 10 to the negative 17th newtons, which is really, really small. But remember, an electron is really, really small as well. So you don't need a huge force to make that happen. And we are going to solve for the strength of the magnetic field. Okay? It's good to note that it's perpendicular. All of these have to be perpendicular to make that equation work. The next problem I'll do is not perpendicular, so I'll show you how to do the trig function part. So we're just going to solve for B using this. Notice that I started a little factor label thing over here. That's because all of these have to be in standard metric units. Coulombs are standard metric units, so that's good. Newtons are standard metric units. Okay? So there's 1,000 meters in 1 kilometer, and in 1 hour, 3,600 seconds. Do the math for that real quick. $72.2. Okay? Then we'll put these 3 numbers into the equation right here and solve for B. So 3 F equals Q V B. 3 times 10 to the negative 17th newtons is the force. The charge, 1.6 times 10 to the negative 19th coulombs. The velocity, 72.2 meters per second. And then we'll solve for B, which is going to be in Teslas. That's just an abbreviated unit for, if you actually, for extra credit, if you want to boil Teslas down into its component units, you could do that. In other words, just solve the units for Teslas, and you'll have some stuff that will cancel, because remember, a Newton is a kilogram meter per second squared. So if that sounds fun, go ahead and do that. Solve for B. We should have .6. With 266. Okay? So yeah, if you didn't know the charge on an electron, that was a little hard to solve. That was number 4, 21A. So let's do number 3 from 21B. This is some power lines that are across a fjord in Greenland, 5.376 kilometers. If this length of wire carries 12 amps and experiences a 3.1 Newton force because of the Earth's magnetic field, what is the field in that region? This does happen, by the way. Remember that we're interacting current-carrying wires and existing magnetic fields. I've actually done a demonstration, if we have time we could do it in this class as well, wherein we take a galvanometer and attach it to just a regular old extension cord, and it works better if you have like a nice heavy gauge, thick extension cord. So just take the extension cord and plug it in to this. That's it. And then spin it around in the Earth's magnetic field, and you can actually get it to deflect, to produce current. Why would that happen? So I'm just basically spinning an extension cord like it's a jump rope and hooking it up to the galvanometer to see what happens, okay? So nothing else is plugged in. We're going to just spin it like a jump rope. Why would it produce current? It has something to do with changing magnetic field. What you're doing is you're changing, by spinning it, you can't ever spin it in exactly the same exact shape, right? So that loop that you create with the wire actually captures a magnetic field. And because it's changing, because we're not like perfect at spinning jump ropes, it actually produces a little bit of current when you do that. That's how generators work, right? You put gasoline in a generator to make something spin, something in a motor spin, and it's a magnet. So when you spin a magnet, like when I plunge the magnet into the coil, you can make electricity, or you can go the other way, make electricity to spin a magnet, which turns it into a motor, okay? All right, so this question is sort of asking that. If we have a power line that is in the Earth's magnetic field, you're going to solve for that magnetic field strength of the Earth. Okay. So we are given the length of the wire, which is 5,376 meters, or 5.376 kilometers converted, so we can have standard metric, right? So 5,376 meters is the length of wire over the fjord. And it has a current of 12 amps. And the force due to the Earth's magnetic field that wire feels is 3.1 newtons. We want to know what is the strength of the magnetic field in that region. And there's one other thing. The wire is at a 38-degree angle with the field. So theta equals 38 degrees. And I'm going to draw a little picture off to the side here. It says it's a 38-degree angle. The wire makes a 38-degree angle with the field. So let's say that these are the field lines. Okay. And we almost always draw magnetic field lines as more than one line because it's a field. If it were just a single line, it wouldn't be a field. It'd be just a single vector, right? So that's usually why we do that. And we have a current-carrying wire. We don't know which way the current is going, but that's not really critically important. We know that it makes a 38-degree angle with the magnetic field. So can you tell me where that 38-degree angle will be? Yeah, everybody go like this. I'll have no idea if you're right, but yeah, it's this angle right here. It's the angle between the wire and the magnetic field, and it's the closest angle, and it's less than 90, right? So are those the angles that you chose? Okay, you were right. So that's 38 degrees. Now, since we need, this is current I, since we need the perpendicular component, will that be The vertical component of the orange line or the horizontal component of the orange line? Vertical, correct. When I just gave you the example of making like a jump rope in the Earth's magnetic field, because it's not going to be perfectly perpendicular or perfectly parallel. You all right over there? Oh. Josh. Did you have something nasty for breakfast? Oh, attaboy. So we're going to find this component, and we're all going to breathe through our mouths. This component will be the sine or the cosine component given the 38 degrees. Stay with me here.
Yeah.
Which one, sine or cosine? Sine, yeah, good. So we want this component. Parallel component, by the way, does exist. This component right here does exist. What effect will it have if it's parallel to the magnetic field? Starts with a Z.
0.
Right. So even though that exists, it doesn't do anything. It does not interact with the field. So yes, this will be the sine component, so I'll just write sine over here, sine of theta. All right, now back to the equation. Since we have current this time, we're going to use I, L, B. And it doesn't really matter what order you put the sign in. You can put it right here, you can put it right here. Doesn't matter. So the force is 3.1 newtons. The current is 12 amps. The length of the wire, were we given that? Oh, that's this up here, the very top thing. I missed it, sorry. 5376 meters. I'm going to throw the sine of 38 in right now. It doesn't matter where, to make that perpendicular. And we're solving for B. Okay? So that's about as complicated as they're going to get. All right, what I'd like you to do is practice. I'm going to give you a couple more problems to practice. And then toward the end of the hour, we'll talk about centrifugal force and parallel wires, some other applications for this. Autumn.
So I understand like the equation, but for logic's sake, are we taking the vertical component, perpendicular component of the current?
Yes.
Okay.
Yes. In that picture. I mean, I guess technically if you twisted it, you could be taking the perpendicular component of the magnetic field. It doesn't really matter. You would do, you end up, mathematically it'll end up with the same thing. Does this picture make sense?
Yes.
Then yes, you are taking it of the current. Yes, absolutely. Yep.
Now what if the field is going down, so then would you ever have to use the sine?
Yeah, it depends on where the angle is positioned. So yes, it is typically the sine, that's usually, but